So in section 10.5, we're going to be talking about a new type of circle vocab word, which is tangent. And so a tangent is probably new to most of you. So I'm going to give you the definition and then kind of show you how it works and a couple theorems that have to do with tangents. So a tangent is going to be a line, and it's going to be in the same plane as the circle. So it's a line in the same plane as a circle that intersects the circle in exactly one point. So unlike a chord that intersects in 2 points because it starts and stops on a circle, a tangent takes a circle and it hits it one time, so it stays on the outside of the circle instead of ever going on the interior. So this is called a tangent line right here. And then when you have a tangent line, you end up getting a point of tangency, and that is the point at which a tangent line intersects a circle. So this right here is the point of tangency. So anytime you have a tangent line that intersects a circle in one point, it will create a point of tangency. Okay, normally we would talk about common tangents, but we're going to skip those this year for time. So we're going to go down here to some theorems that have to do with tangents. So first of all, this theorem comes from the idea that the shortest distance from a tangent to the center of the circle is the radius drawn to the point of tangency. So let me show you how this works. This line is tangent, and here is the radius intersecting the tangent line at the point of tangency. That distance right there is the shortest distance from the center of the circle to the tangent line. So if I try to go over here and draw a different distance, it's going to be longer, so the radius is the shortest. All right, so that brings us to this first theorem. So in theorem 10.10, it says, if a line is tangent to a circle, then it is going to be perpendicular to that radius drawn to the point of tangency. And so we just talked about that being the shortest distance. So there is going to be a right angle formed when the radius intersects the tangent line at the point of tangency. And then you might notice it says if and only if. That's because this theorem works both ways. So if your radius intersects a line and makes a right angle, then that line has to be tangent. Okay, so I'm going to show you a couple questions that deal with that theorem. So first of all, we're going to actually determine whether or not this is a tangent line question. So the answer is going to be either yes or no if the line is tangent. So if this line right here, and it doesn't show the whole line, but if I drew the whole line, they want to know, would this line be tangent to the radius? Okay, so if it's tangent, then there needs to be a right angle, but I'm going to put a question mark because we don't know if there's a right angle there or not. So what I'm going to do is I'm going to do Pythagorean theorem and see if it works. If it works, then we know we have a right triangle. So we did this last chapter. Okay, keep in mind your radii of a circle are congruent, so that will be 6. And I'm going to set up, does 8 squared plus 6 squared equals, and then keep in mind this entire hypotenuse would be 18 if we add those together, 18 squared. And that's a question mark. We don't know if it does or doesn't. So we're going to add that up and see if it works. So this is going to be 64 plus 36 is 100. Does that equal 324, which is 18 squared? And that is a no. So if these are not perpendicular to each other, the radius and the tangent line, then that is not a right angle. In fact, this would be an obtuse triangle, not a right triangle. And so what would happen is we'd have to say no, the segment is not tangent to the radius. And keep in mind, they're just using a piece of the tangent, which is the segment. So that is a no. All right, so you are going to, after the video, go back and try this one, which is going to be another practice question to see if you can do one on your own, and you'll check your answers on Canvas. And then I'm going to show you a couple more examples that are like that, but we're going to use the theorem in the opposite way. So this time it's not asking if it's tangent, it's saying assume that the segments that appear tangent are tangent. So for instance, if this is a segment that appears to hit the circle in one point, you're going to assume that's tangent. Same thing here. If this segment appears to hit the circle in one point, we're going to assume it's tangent. And those are just pieces of the tangent line. All right, so if this is a tangent segment, and this is a radius that hits the tangent segment at the point of tangency, you can go ahead and insert a right angle into that picture. So what we're going to do is we're going to use Pythagorean theorem to actually solve for the radius. So these are my legs, and that's my hypotenuse. And yes, this piece would be x also, but we don't really need it because we have the whole hypotenuse. So we're going to set up x squared plus 14 squared equals 17 squared. And we're just going to solve this. So when we do 17 squared and we minus 14 squared, we're going to get x squared equals 93. And then we're going to square root both sides. And we're going to look for perfect squares that go into 93, but nothing goes into 93. So we're going to leave it as an exact answer in radical form. That is the length of the radius using this theorem over here that says a radius and a tangent have to form a right angle at the point of tangency. All right, so I'm going to do one more example because this one's a little bit harder. So this time, I'm going to still look for the right angle. So here's my tangent line and here's my radius. First thing you want to do is put your right angle in the picture where the radius and the tangent line hit each other. Then I'm going to notice that if this radius is x, then this radius is x. Now, unlike the question I just did where I didn't need that radius, I do need this radius right here because it's one of my legs. All right, the other thing I'm going to notice is the hypotenuse when I put these together is not 2x, it's x plus 2 or 2 plus x because you're combining them. All right, so this one's going to be a little more intense. We're going to take the legs, x squared plus 4 squared, and that is going to equal the entire hypotenuse, which is x plus 2 squared. So you might start recognizing what we've been practicing on the quadratic review. We're going to have to FOIL this. So x squared plus 16 equals. This means you have two of them, so you have to write it twice. You can't just write x squared plus 4. That would not work. You have to write it twice in FOIL. So x squared plus 16 equals, okay, so I'm going to FOIL, x squared plus 2x plus 2x plus 4. So this is first, outer, inner, last. So now I get x squared plus 16. I'm going to combine my like terms, x squared plus 4x plus 4. And then I think I might have to factor, but when I go to subtract the x squareds to be on the same side, they actually cancel each other, which is nice. So we're going to be left with 16 equals 4x plus 4. You're going to minus the 4, get 12, and divide by 4 and get 3. So if your radius is a variable and you don't know how long the hypotenuse is, like this one, you will have to set up a question where you FOIL and then solve, but it will always work out where you'll end up getting 1x and your x squareds will cross out. So you are going to try at the end of the video, you're going to go back and try this one. This is going to be another foiling one, and so that'll give you a chance to try it on your own, and then you can check the answer on Canvas. Okay, another theorem that we have with tangents, so all these theorems have to do with tangents, is if you have an exterior point and you have two tangents coming from the same point. So these are tangent segments, which are pieces of a tangent line like we've been using. This is a tangent segment because it hits in one point, and that's a tangent segment. It says that they are going to be congruent if they both start at the same point. So this piece will match this piece. And by the way, we can use this theorem, kind of like the other things, in a couple different ways. So let me show you the first example down at the bottom. So for example 4, it says, assume that segments that appear tangent are tangent. All that tells you is that these segments are hitting these circles in 1 point each. All right, so let's just focus on this picture. So these tangent segments both start at T, so that's going to make this tangent segment match this tangent segment using that theorem up there. Now I'm going to cover up this circle, and if this tangent segment has a tick on it, this one will also have a tick because they are going to be the same length if they're both coming from T also. So what this does is it says these three tangent segments have to match each other. So in order to find x, I'm going to set 3x minus 8 equal to x plus 10, and once I solve, I'll know my x. So this is 2x equals 18, x will be 9. So that's one way to use the theorem. Okay, on the back, you will try this one after the video and check your answers on Canvas. And then I'm going to show you one more set of examples using that same tangent theorem. But we're going to review circumscribed. So we kind of introduced this term to you in an earlier section. A polygon is circumscribed about or around a circle if every side of the polygon is tangent. So if you look, my circle is hitting each side of the polygon one time. These are all tangents to the circle, so that is considered circumscribed. Again, these are all tangent to each side of the polygon, or the circle is tangent to each side of the polygon, so that is considered circumscribed, and the same thing here. And then you can see how these don't work because you don't have, like, this side is not touching, and then this is not, the circle is not touching each side. All right, so as long as I know that the circle is touching each side of the polygon, then I know that I can consider it to be tangent to the circle. So using that idea, we're going to take this circle, which is inscribed, and this polygon, which is circumscribed, and I'm going to put dots on every time the circle hits one of the sides of the polygon. Those are all points of tangency. All right, now, if I have an outside point and I go to the circle, these different segments from the same outside point have to match using the theorem that we just talked about on the other page. So if this is x, this one will be x also. Okay, same thing over here. If they both come from u, ub and uc have to match. So if this one's x also. All right, same thing. rd has to match rc because they're both coming from r. So if this is 3, this will be 3. And then again, if I'm coming from S to A and S to D would match. So if this is 3, this is 3. All right, so what they're saying is the perimeter of the entire polygon is 18. So I'm just going to go around and add everything up. So these two would be 2x, plus I have another 2x there, plus I have 3, 3, 3, and 3, which is 12. So when I go around the entire polygon, I get 4x plus 12 equals 18. And that's going to equal 18 because the perimeter is 18. So 4x plus 12 equals 18. 4x equals 6. And x will be 3/2 or 1.5. Using that same theorem where the tangents match if they're coming from the same outside point. Okay, so even though this one says u, I'm going to do one more with you. So again, as long as this polygon is circumscribed, then these are all points of tangency every time the polygon hits the side of a circle. So from Q, if these two pieces match, because they're both coming from Q to U and to T, then I know 14 has to equal 2x, so x is 7. So right away I know the value of x, so I got that part done. Now I'm going to come over here, and I don't have anything up here, so I'm going to skip that for a second. I'm going to come down here. If this piece is 17 from S to T, then from S to V, that will also be 17. Well, this entire segment's 27, so R to V will be 10, and if R to V is 10, then I know that R to U will be 10. Okay, so now what I'm ready to do is find the perimeter. Keep in mind, this is now 14. Okay, so I'm going to add up 10 plus 10 plus 17 plus 17 plus 14 plus 14, and that's going to give me my perimeter. So that's like 20 plus 34 plus 28. So that gives me a perimeter of 82, and I'm just going to put inches because the units were in the problem already. So those are all theorems about tangents. So what I would like you to do is you're going to skip the constructions at the bottom, and you are going to go back through and try the questions we skipped and then check your answers on Canvas.